All right, now let's go over a full example to see the whole process of defining a neural network, training it, and then using it to make predictions. So the task we'll have is to use a neural network to model a sine wave. So this is our target. This is the function we're trying to learn. And we'll start by defining the architecture of our neural network. The way we'll do that is using something called modules. So the base class for pretty much all the layers of neural networks in PyTorch is something called nn.module. And this module basically represents the building block of the full computation graph. So typically, your neural network might have things like convolution layers, fully connected layers, pooling, things like that. And each of those is a subclass of nn.module. And those three actually have already been defined for you in PyTorch. So when you want to define your neural network, you would just piece together a bunch of these modules into your own module for the overall network. So as an example, let's take this model, which we sort of saw in the first video. So we have three operations. The first two are linear, followed by nonlinearity. And the last one's just going to be a linear transformation to get a scalar output value. So this is the architecture we're going to use for this problem. So in order to define this architecture, we're going to define a class in Python. You can call it whatever you want. We'll call it net in this case. But the important thing is that we want it to be a subclass of nn.module. So what you're going to do is you typically need two things within your class. In the constructor, you're going to define all the layers of your model. And in this forward function, you're going to define what it does on an input and return some output as the prediction. So in our constructor, we have three layers we need to define, 1, 2, and 3 over here. So we're going to define those as FC1 through FC3. And each of those is going to be using a built-in nn.linear class, which is a subclass of nn.module. And we can specify what we want the inputs and outputs to look like. Then for the forward pass, we're going to define what PyTorch, what this model actually does to make a prediction. So here we're going to send it through a linear layer, then a Rayleigh nonlinearity. Do that again a second time for the second hidden layer. And then for the last layer, we're just going to do a linear transformation and then return the output. So once this has been defined, you can initialize instances of your network, just like you would with any Python class. And when you print it out, you can see this nice representation of what your neural network looks like. And you can see all the layers, you can see their names, and you can see what their input and output shapes are. So when you want to actually evaluate this neural net on some input, the way you should do it is by calling it directly and passing an input. So we initialized a variable net. We're going to call it directly and pass in x. You want to be really careful not to call net.forward x. Like we're not just going to be calling the forward pass of this class that we defined earlier. Don't do this. And the reason is because what calling net directly does is there's some like initial setup code that's taken care of for you, and then after that it like actually calls net.forward. So you don't want to ever call forward directly. You want to call the module and pass in the input. And so once we do this, we can see that the output is just a tensor that has, for the first dimension, the same length, because this is the batch dimension. We passed in 100 inputs and we get 100 outputs. And the second is just the output size that we defined earlier in our neural network. So now we can visualize what this network looks like before training. We have our inputs, we have our outputs. And so this is like what our randomly initialized model is predicting for these values. So if we dive a bit deeper into like what's happening within this nn.module, each time you define an instance variable that's some kind of module, And when this is done within the nn.module class, what it does is it considers it a parameter of your module. And the reason that's significant is because these parameters will automatically have their gradients tracked. So requires grad equals true. So if you print these out, you can use this function called named parameters, or parameters if you just care about the values and not the names. And you can see what layers or what tensors make up this model. So we had 3 fully connected layers. Each of those fully connected layers has 2 tensors to represent the operation, one for the weight and one for the bias. And each of these parameters, both the weights and the biases, will automatically have their gradients stored, like we said earlier, because they were defined inside of the nn.module subclass. So if you print something like this out, you'll see that it has a grad, but in this case it's still none because we haven't done backprop yet. One common mistake is if you're ever trying to define a list of modules, for example, if you want to define a neural network with an arbitrary number of layers and you maybe use a for loop to define your individual layers, you don't ever want to just like add them to a regular Python list like this. Because if you do that, PyTorch won't recognize that these are actually submodules, and they won't be considered actual parameters of your module, and their gradients won't be tracked. So instead, the way to do that is by using this class called nn.modulelist and passing in the list of layers that you actually want to use. And if you do it this way, then network 1 and network 2 will both have their gradients tracked properly. So when you make that prediction, so earlier we did y equals net x to make a prediction. So when you do that, the output is just a tensor, and you can perform operation on the tensor just like we did before in all the previous videos, and it'll automatically track the computations and let you compute derivatives. So here, for example, let's use a squared loss on our predictions and the target. And when we call loss.backward, that's going to automatically run backprop for us and populate the gradients of each of the weights of our model. So we can now go into the .grad property for each of the parameters of our model, and we can manually implement gradient descent by basically like taking a step in the opposite direction of the gradient. And remember we talked about this before, if you call backward multiple times, it's actually going to keep accumulating the gradient. So if you're going to do gradient descent, after you do this step, you have to always make sure to zero the gradients so that next time you start with a fresh copy. And so at this point, we pretty much have all the pieces we need to train our network. We can just use a for loop and do this repeatedly. We compute the loss, call backward to do backprop and populate the gradients, and then adjust each of the parameters using the gradients that were filled in. And then we zero the gradients and start over again. So with that, we can get a network that models something pretty close to our sine wave. So it definitely is learning. But this implementation is kind of annoying to have to write out every single time. So PyTorch has some helper functions basically that take care of certain things for you. And so we'll slowly add those things in and see how that simplifies our training process. The first thing is loss functions. So PyTorch has a bunch of built-in loss functions. And again, these loss functions are modules, just like any other layer that you had in your model. And you can pass your data through them. So let's say instead of manually implementing a loss function, we define our loss function to be the mean squared loss. And we can pass in like the outputs and our targets, and we get some tensor as our output prediction. So now we have the same thing, except we've just replaced the loss with loss function. And you can see that it will pretty much end up doing the same thing. So it's not really a big deal here because our squared loss was pretty easy to implement. But if you ever want to like experiment with more complicated loss functions or make it really easy to just like plug in arbitrary loss functions to see what works better, this is definitely a good practice to follow. The next thing is optimizers. So we'll also use the optim package within PyTorch to use some of the built-in optimizers they have instead of having to manually implement gradient descent like we did before. So what we'll do is we'll start over, redefine our neural network, and here we have an optimizer. And here you can pretty much use any optimization function you want. You can use SGD, which would most closely match what we were doing before. You can use RMS prop, or in this case, let's just stick with Atom. So it's easy to like plug in different optimizers you might want. And here, okay, so let's make some predictions and then see what the network looks like before training again. So again, we've reinitialized it, so we should have some random values. And now, instead of manually implementing gradient descent, we'll replace it with the optimizer. So the way that it works is you compute your loss as usual, but you'll do all optimizations through the optimizer. So first you'll call optimizer.zeroGrad, which zeroes out all the gradients. Then you do loss.backward to populate the gradients of each of your parameters. And then finally you do optimizer.step. So optimizer.step is kind of equivalent to this code that we wrote, which basically updates each of the parameters using a step of gradient descent. And this optimizer.zeroGrad line is basically the same thing as this part of the code, where we make sure to zero the gradients each time so it doesn't accumulate. So just one thing to be careful of, when you initialize the optimizer, you want to make sure to pass in all the parameters of whatever neural network or neural networks you're trying to train. Because this is the only way that the optimizer actually becomes aware of what it's doing gradient descent on. So when you call like optimizer.zeroGrad and optimizer.step, it'll only actually update the gradients of the parameters that you pass in here. So if you have a single neural network like we do here, it's really easy. You just pass in net.parameters. But if you ever start working with like multiple models that are kind of training simultaneously, you just want to be careful to make sure that you've actually given the optimizer all the parameters. Okay, so now let's run this code. And we can see that it did exactly the same thing that we had before, except now our code is much more concise. So here's a summary of what we did. Feel free to pause the video and or go back into the collab and just make sure that you understand what this whole training process looks like. Next, we'll talk about GPU support in PyTorch. So most of the time, you'll probably want to do your training on a GPU because GPUs are optimized for matrix operations, and it'll make your training run much faster. PyTorch makes it pretty easy to move your tensors between CPU and GPU to actually do that training process. So we'll see an example of what that looks like here. First, you'll want to check to make sure you have a GPU available on your current machine. So a lot of you might end up running your homeworks on Colab. Colab is nice because it gives you free access to GPUs. If you're going to use Colab, just make sure that you go into runtime, change runtime type, and just make sure that you have GPU selected. Otherwise, it's not actually going to be training on GPU. So once that's set, we can print and we can see that torch.CUDA is available is true. And here's an example of how we can initialize a tensor on GPU instead of CPU. So by default, if you define some tensor like torch.ones, it's going to be on CPU. But we can specify a device parameter and tell PyTorch that we actually want it to be initialized on GPU instead. And you'll notice here it'll specify the device if it's on something other than CPU. One thing that you really want to be careful of is you can only do operations on tensors if they're actually on the same device. So this code will error because we have X, which is on CPU, and Y, which is on GPU. If we try to add them together, we get this error message. So if we wanted to combine them together, we would have to maybe move x to the GPU. And the way we do that, if it was originally initialized on CPU, is using the to function. So we just use x.to and specify that we want to go to GPU. And this way we can add them together properly. So kind of like you can't convert tensors that have gradients being tracked into NumPy arrays, you also can't convert tensors that are on GPU directly into NumPy arrays. So if I do this, I'm going to get an error. So instead, if you want to convert to NumPy, what you're going to have to do is first move it back to CPU and then convert to NumPy. Yeah, so that kind of adds like another layer of complexity you have to think about when you want to convert tensors to NumPy arrays. You have to make sure that they're detached so they don't have a gradient. You have to transfer them back to CPU, and then you have to convert to NumPy. So this can sometimes be kind of like a headache to track. So we have this nice utility function that will be available to you on all the homework assignments. It's called ptu.fromNumPy and toNumPy. And basically what that will do is from NumPy will convert a NumPy array to a PyTorch tensor that's on GPU. And toNumPy will, given a tensor that's on GPU, it'll first move it to CPU and then convert it to NumPy. So if you use these two functions, you don't really have to think about whether you're using GPU or not anymore. If it's supported, then it's going to do all of your tensor operations on GPU. Okay, so now that we've learned a bit about GPUs, let's try to incorporate this into a full training example on that same sine wave task from before. So this is the full flow of training a model. Everything is pretty much the same as before, except a few sections are new. After defining the neural network, this is something that you're going to have to add in if you want GPU support. So basically you define a device. Usually it's good practice to define it this way, where we say if it's available, then we'll use GPU. If not, we'll use CPU. That way your code is still compatible either way. And then we're going to want to move both our neural network and our targets to that new device. Usually in practice, you're only going to move the neural network at first. You're not going to move all the targets because you might be working with like a huge data set, and it's not feasible to put it all on GPU at once. Instead, what you do is work with them in batches, just like when you're doing stochastic gradient descent or mini batch gradient descent. And within the for loop for your gradient descent code, you can move each individual batch to the GPU separately. But here, since we have like a pretty small set of targets, we'll just move them all to the GPU at once. And the other thing we added is here in the training code, we move our input from CPU to GPU. So normally this is where you would do something like yTarget equals y.toDevice. yTarget.toDevice. Everything else is pretty much the same as before. And we can run this code, and you should notice that it trains a lot faster. The difference will become much more significant if you start working with things like images or higher dimensional data. Right now, it's kind of a small difference, but you'll definitely want to use it on all of your homework assignments. So now, moving on with our example, we're going to evaluate the model. This is usually what you would do to make predictions with a PyTorch model. So notice there are two things we added here. First, we want to do net.eval. What that does is it switches the network to evaluation mode. It doesn't matter for our example, but if your neural network has things like dropout or batch norm, where it should behave differently during training and test time, you definitely want to make sure it's in evaluation mode so that it doesn't give you inconsistent results. And the next thing is with torch.nograd. This is a nice helper function that you should use when you're making predictions. And basically it says that everything within this block, any tensors that are in this block, they're going to have their requires grad property set to false. So since when we're actually doing evaluation, we're not going to be doing backprop. We don't care about tracking the gradients. So this is kind of like a small performance improvement. We tell PyTorch that we don't care about the gradients within here. So this second thing is maybe less important. This will make your code a little more efficient, but even if you forget it, that's fine as long as you don't accidentally like call backward on anything. But this net.eval is really crucial, especially if you're doing things like dropout. Otherwise, your results are just not going to be correct. So now we have our predictions in the variable y. And remember, since these are on GPU, we want to first convert them to CPU, and then we can call numpy to convert them to numpy arrays. And we can see that it did pretty well. The last thing you'll do after training and evaluation is probably you'll want to save your model weights so that later on you can use this trained model to do something else. So the way that you save models in PyTorch is that you basically take your parameters and you store them in a dictionary that gets serialized into some kind of file. So here we're specifying a path for our checkpoint. The convention is usually to make the file extension .pt for PyTorch, but it's not a big deal. You can call this whatever you want. Then we have torch.save. So if we call net.stateDict, that gives us a dictionary of not only the parameters of the model, but also anything else that's important for making predictions. For example, if you have a batch norm in your model, it's going to keep track of like the running mean. So that's where stateDict is slightly different than parameters. When you're saving your model, you don't just want the parameters, you want the entire state of the model. So we're going to be saving this dictionary to this path. And then let's say later on you come back and you want to load this checkpoint back into your model and make predictions again. So what we'll do is we'll initialize a new model, make sure it has like the same architecture as before, and then we'll call load state dict, and we're going to pass in the result of loading that file that we saved to earlier. And then don't forget to call eval if what you're going to be doing is evaluation. So if we run this, we can see that let's see. Huh. Oh, I see. Okay. Well, all right. Let's just put them both on GPU, and now we can compare their parameters, and we'll see that the loaded checkpoint has the exact same names and parameters, all the values as the original model. To summarize, what we did was we started by training the model with our loss function, optimizer, and the neural net we defined, making sure to move everything to GPU if that's what we want to train on. We evaluated the model, making sure to set it to evaluation mode and turn off the gradients. And then finally, we saved the model weights to some checkpoint file so that later on we can load it and use it to make predictions again.